So good afternoon, everyone. Welcome to our June method seminar series. Today we have one of our core scientists, mentees, Dr. Jeffries. She'll be presenting on inconsistent and missing data, a Bayesian approach to handle both simultaneously. So I'm very excited to welcome her, and I'll turn the floor over to her. Welcome.
Definitely, thank you guys for having me. Well, exactly. Yeah. Exactly. This is. I promise I won't spill it. So interesting. There we go. Awesome. So just quick overview of what I'm talking about today is I'm going to give you, I guess all know what self-report surveys are, but talk a little about imputation and data editing, and brief introduction to the motivating data set behind some of this work, the analysis of this data set using these methods I'll be talking about, and then some comparisons between standard techniques and using this different method. So, in your field of research, you guys all know what self-report surveys are, and the type of data that can be generated from them. They're behavioral studies, or the teacher surveys, or the census, and they're always subject to some sort of missing data or some sort of inconsistently or erroneous data. So some of the reasons, we don't always know why the data are inconsistent or erroneous. It could be the participant not understanding actually what you're trying to ask from the question. It could be a failure to recall a question you asked them, what'd you do 5 years ago? Or it could be even presentation bias, where they're trying to choose what they think the most socially acceptable response is. So we don't always know why the data perhaps give conflicting responses. So the common solutions to handling missing data is to impute missing data, and you edit inconsistent data. So imputation is the process of adding data where there was none before, where editing changes the data from one value that you deemed for some reason as being inconsistent or wrong to a value that you deemed being correct. So we know that if you've done a lot of imputation, you know that it can artificially increase the sample size because you are adding data to it, which can artificially reduce your standard errors of the results by that increase in sample size. And that the method used to do the imputation is important. For example, if you take the average values of all your observed values and use that mean as your imputed value for all of the missing data, you're going to bias your variance of your final result towards 0. So any imputation and editing process should contain some sort of random component to it, so that every value you're filling in or changing is not being changed to or imputed as the exact same thing across the board. That's if you just do regardless if you do a single imputation, you're setting that's you're still not accounting for the variance that is, or the uncertainty in that actual imputation process. So what is commonly used is the multiple imputation, where you start off with a set of incomplete data. You perform some imputation process that has a random component to it. You do it multiple times, so you have multiple complete cases, or multiple complete non-missing data sets, which you perform an analysis on each one of them, get your results, and you pool them according to a certain set of rules to have your final results, where these results account for your within imputation variance and between. So multiple editing is a direct parallel process to that, where you have an editing process that has some sort of random component to it. So you have a set of inconsistent or incorrect data. You perform the editing process multiple times to create multiple correct data sets, which you perform your analysis on, pull your results at the end. So imputation, some of the more commonly used imputation methods, again, is using model-based imputation, where you're using information from other variables available in the data set to inform your imputation. But editing, most commonly, is just to either blank out the conflicting data, you make it missing and then use an imputation method, or you set up a series of logical edit rules. If they said A here and B here, well, I'm going to change B to A because I don't believe B. But in general, multiple editing is kind of a commonplace practice for, or at least it's an accepted technique for handling missing data, where multiple editing is not. But I'm going to try to convince you that at least it should be considered. So, I mentioned that the framework of this is done under the Bayesian paradigm. So that again treats all missing data, whether it's parameters or all unknown parameters, whether it's missing data or regression coefficients, as unknown, which means they all have distributions associated with them. And Bayes' theorem gives us a relationship where we can describe we can make some inference regarding those unknown values based off of what we do observe, given those unknown parameters and a little bit of prior knowledge about those parameters. And it's done so by we sample from this posterior distribution, so it's a sampling technique.
You can leave it here. It's actually more of a comment on an earlier slide that said that imputation can artificially reduce standard errors by increasing the sample size. And I tend to think of it as, in a Bayesian framework, similarly, that I'm not wild about the term adding data, because you're just trying to represent available information in the data. You're trying to represent typically patterns of association between variables. And it is possible that imputation will reduce standard errors. It's also possible for it to increase standard errors. That depends on how well predicted the missing values are from the observed values. So I agree with the next point, especially if you say like the method used to represent available information is important. And I agree with the next point, single imputation would bias the variance results incorrectly towards zero, because that doesn't accurately represent uncertainty in a Bayesian framework. So anyway, it's just kind of endorsing what you're doing, but representing that I'm the son of a lawyer.
Understood. Appreciated. Clarity is always very important. So I'm not, other than just reminding or mentioning that this is done under the Bayesian paradigm, I'm not going to get into a lot of the details about the nuances of the sampling and stuff that I've used. So this methodology that I developed as part of my dissertation, I call it the Sequential Bayesian Regression for Multiple Imputation and Conditional Editing. Cyber mice have to have something. I'm Rob's student. You have to have something catchy.
Come up with a cool name. That's half the battle.
Yes. No, we went round and round on this. So it's a model-based approach that will multiply impute the missing data while also editing the inconsistent data at the same time. It correctly propagates the error that you're incurring by applying a random editing or imputation process, and it's variable specific and very customizable, and that the regression model is your imputation model and your editing model are all variable specific. So this model may be missing in this framework, and this variable may be missing in this framework, and this one may have a different set of inconsistencies, and we'll have examples for those. So it's specific to each variable, and.
So Robin, for each variable, can you come up with specific edit logic rules?
Yes, they're not really rules.
Okay.
They're not, because that implies, logic rules implies deterministic editing, where you do it once and this is the decision and this is always how it is.
Right, so for each variable, I guess kind of going back to like the Bayesian model, so do you basically recall or just collect all the information that you have about the variable and then kind of anticipate what kind of inconsistency there would be, and then correct those inconsistencies
Not-
based on what you know? Or?
Not quite. This technique, it does depend on you recognizing that an error exists. It doesn't really predict an error as it stands.
So
Sorry.
I'm just thinking about, based on our experience on the, you know, the reason behind why there's missing data, there's falsification and all this. So one of the other things that we experienced was like survey conditioning, where a lot of times we're employing the same questionnaire over time, multiple times.
Mm-hmm.
So a good example is like the number of sexual partners that you have. So at baseline, people would report truthfully, I have 10 partners, and then subsequently, when they're getting interviewed, they realize if I say 10 partners, I'm going to be asked like a barrage of questions about my 10 partners. So they they falsify by saying, oh, I only have 2 partners.
Correct.
And then so we have some prior information about and it's hard to know which is the truth. And
Yes.
that's where the edit logic comes in. So I'm
Yeah,
to see.
I have an example of something that fits that kind of example. But the thing is you recognized that this variable is subject. It can only change in one way. It can't really go down. It can only kind of go up. And so that I have an example of a variable exactly like that.
Okay.
But you had to recognize that this is a problem. This could be a problem for this variable. And so you set up a model for that.
Okay.
And the whole learning from previous information, that kind of comes from, because it's a cyclical model, so I run through all the variables once, create estimates, and then use those current estimates in the models for the next set. So if we, just a real quick specifics, if we consider just 3 generic variables that are subject to both missing and inconsistent data, for each cycle, I'm going to fit a model on the most current version. So we're looking at cycle L right now, the most current version of the data for Y1 using the current values for Y2 and Y3, which happen to be from the previous iteration. I'm going to perform some kind of I'll edit the inconsistent and impute the missing values for Y1 and generate a new vector for Y1 that's complete and consistent. So no missing and no inconsistent data. And then use that in a model for Y2, and we're still using the most current versions of the data, so we're using the Lth iteration of Y1, but the previous version for Y3, because we haven't gotten there yet. Perform editing and imputation models on Y2, generating an updated vector of Y2, do the same thing for Y3, edit the inconsistent, impute the missing Y3, and then now we have a full set of complete and consistent values for each of the variables, and we use that to restart the next loop. We're now on iteration, cycle L+1. So that's the bare bones basic idea behind the cyclical or sequential nature of this. So a little introduction on the motivating data set. It was Project Connect was an 8-year longitudinal intervention study aimed at reducing teen pregnancy and HIV and STD rates among high-risk, specific target schools. So it's only teens who go to these schools in these high-risk areas. And the effectiveness of this intervention was assessed by handing out a survey every year to these students. And the design of the study was part longitudinal, so we followed certain kids across years, and then additionally sampled cross-sectionally across years other random students. So students could participate anywhere from 1 to 4 years. The survey itself, the project staff went into the classroom and handed the kids a 40-page paper and pencil survey in a classroom setting where not everyone in the classroom was participating, because either they opted out or their parents told them they couldn't do it. The teacher may or may not be in the room, so there was a little bit of sharing, and confidentiality wasn't necessarily protected in terms of privacy. But there's no way to enforce that the skip patterns that were on the piece of paper were understood and followed. It was a pretty comprehensive survey, demographics, health indicators, but also some sensitive subjects like sexual behavior, sexual activity, and substance use. And again, to try to preserve confidentiality, every student who was in the classroom got the survey, regardless if they had participated before. So it allowed people to report the exact same question on multiple surveys, like their gender, or like, not really here. Well, no, we did ask the high school students the number of sex partners. Things that you shouldn't necessarily stay constant over years, but so it allowed inconsistent reporting by allowing a paper and pencil survey and allowing students to report on the same questions across multiple years, allowed them to make inconsistent reporting patterns across years, but also open the door to fixing these errors using a statistical method. So I identified, or I'm going to talk about 3 specific types of inconsistencies that I found in this data. The first is when we're looking at time-fixed variables, variables that should not change or cannot change over time. Their birthplace, their birth date, gender, and this is adolescence, and we're just assuming that the transgender or sex change is a non-issue for this population. Then there's the inconsistent monotone longitudinal. This is where you have that structured trend, like age can only increase. They can't report they're younger on a following year. It's also the lifetime questions. Have you ever smoked a cigarette? It can only go from no to yes. You can't go from yes to no. And then there's the combination of responses. When you have multiple responses, multiple questions asked in the same survey that give different information or give conflicting responses. Like, have you ever had sex? No. Have you had sex in the past 3 months? Yes. One of those 2 is wrong. So for the Project Connect, it just employs a series of logical if-then-else rules. I mean, it's a good page and a half, and it's order specific. It has to be done in this order. And those edit rules are only pretty much for a single year, looking at each individual year by itself. For a couple of the time-fixed variables like birthday and gender, we applied a majority rules. If they said they were male 3 out of 4 times, then that record for that student, or all of the surveys for that student, got set to male. We did try to consult school roster data, but it's not a gold standard. The schools get a lot of things. They're just as conflicted as the students. But there's no editing pattern or no editing rule in place for the longitudinal, or for the inconsistent monotone ones, the age, the ever lifetime type questions. There's no rule in place. And there's no measure of uncertainty applied to these rules. We said, if they said this and this, we're going to change it here, and we're right 100% of the time for 100% of the participants. Scientists, I mean, you guys know what you're doing. You know the literature, you know the subject material. So I'm not saying these rules are bad or informed, but they may not be 100% correct for 100% of the time. So the 5 variables specifically that I'm going to look at and demonstrate in this model, the 2 of them are the inconsistent repeated measures that we're looking at gender and birthplace, having ever had sex as a monotone longitudinal response that can only go from 0 to 1, and then the inconsistent multivariate response patterns. Is questions about the CAP, the Condom Availability Program, which is one of the intervention targets that's mandated in all LAUSD schools. So the question was, have you gone to get a condom from someone on campus before? And do you know that you can get condoms, or do you know of someone on campus that you can get a condom from? And have you gotten condoms from this person before? Or the inconsistent pattern is saying, yes, I've gone to get a condom from someone on campus, but I don't know who I can go get a condom from. So again, one of those 2 is wrong.
It's totally possible.
How? If you've gone up to a physical person on campus, then you know someone.
Well,
we don't ask the names. We don't ask any specifics on this. It's like, do you know that someone?
You have no idea.
Hopefully this is during school hours, and this is high school, so hopefully we're not have that.
Yeah, but it's possible.
It is.
But I'm reminded of I was just infuriated at someone over their response to an email. There was like 2 friends who were having a cat fight, and I got caught in the middle. And at issue was whether one had read an email sent by the other before she sent back a rude reply. And the email sent by the other about participating, it was a PTA activity at school. And And she had participated in the activity. And so I was like, that was just outrageous. She participated in the activity, but she sent this rude email. And so I confronted her with it. She said, I didn't read the email. I said, how could you say that when you participate in the activity? She said, I didn't read the email. This other friend told me about the activity. So in other words, there are these, you know, it looked like a contradiction to me. It wasn't. But what you're doing is resolving the contradictions somehow.
Exactly, yeah. And there is kind of a later add-on to this to say, okay, well, you know, maybe they didn't really make an error or something like that. So across the first 4 years of the survey, project staff collected about 36,000 surveys on about 25,000 students. There's a relatively, and most of which were from high school, so there's a relatively low missing rate, an inconsistent rate among the individual student level variables, higher on the survey level utilization, cap utilization and knowledge variables. And I have
You can hold it.
but it's going to go all the way back to the beginning, right?
No, just previous slide.
No. Okay, I wonder if I can do. Yes.
Oh, good.
Sweet. Anyhow, so these percentages are out of, again, these are only asked of the high school students. So we're still looking at a moderate missing rate, but only about a 3% inconsistency between those two variables. So to model these 5 variables, I use a set of fully observed and consistent predictors. You know, most of them are demographics: age at onset when they enter the study. Intervention condition and school-based health center are used in the CAP models because the CAP was a target of the Project Kinetic intervention. Ethnicity, and then whether or not they carried a weapon in the past 30 days and whether or not they fought in the past 30 days, or past year, excuse me. So the cycles for these 5 variables, it's the same, follows the same cycle that I mentioned before, where I'm going to model, edit, and impute gender. Use and then model, edit, and impute true birthplace using the updated values for gender. Model, edit, and impute ever having sex using the updated versions of gender and birthplace. And then I'm going to model and only impute cap utilization using the updated versions of Y1 through 3. And then conditional on them saying that they have not gotten a condom from the cap, I'm going to model and impute cap knowledge using Y1, the updated versions of the previous variables, because these are a joint edit. So I'm going to do the imputation first and then do a joint edit. And since these 3 are subject level variables and these 2 are survey level variables, to complete the loop, I'm going to calculate. I'm just going to aggregate these across for each subject across years, so I can use these new updated variables back in step 1. Now, I'm not saying that I think the cap variables predict gender. They are associated, though.
I have a question.
Yes.
This goes back to a few slides ago when you were describing the process in the abstract. I was wondering, what if your Y1 variable has nothing to do with your Y2 variable, like gender and birthplace, for example? I would expect those didn't have much of an association. So how does one inform the other in that instance?
You'll see.
Great. Thank you.
And it only works, so it's a little, I can't say arbitrary, but I mean, I have this order because of how it feeds in to these models. So, and it's because of the way the models that I've chosen. So for the inconsistent repeated measures model, it's a hierarchical latent variable model. So I have a model for the latent truth and a model for the reporting value. So this reported value is a mixture model where you're going to either have a regression, the effect for how you report is going to be different based off of what your true value is. So how you report being female, the probability you report being female in a survey will have different coefficients for if you're really a male or really a female. It's fine. I was going here anyhow. So
Try just holding your index finger. Just hold it there.
No,
You got it.
I just need to stop. See, this is why. That's fine. I'll learn. Okay. So, either way, it's a mixture model. So the reporting value, the model used to predict how you report the variable of interest will differ based off of what the predicted value for the true value of that variable is. Again, so Y1 and Y2, we're looking at gender and birthplace, they have the same model, the same structure. So I'm going to start by modeling the true and reported gender, and I'm going to use this set of coefficients. So just for reporting, for the reporting model, I'm just basing it off of intercept and age at the time of the survey. And to model true gender, I'm going to use the weapons and fighting variable and then the two cap variables that are now on the subject level. And then the editing and imputation model is I'm going to update this true value for gender based off of whether or not it was consistent reports. If it was inconsistent, I'm going to use the sampled value for the true gender. Or if it's missing, I can also use the coefficients from the regression model to predict the true gender for again at each cycle. So now for birthplace, I add in that variable for gender into the reporting model for birthplace. This allows males to, while it doesn't, gender is not associated with true birthplace, but it could be associated with how they report their true birthplace given what their true birthplace is. Are males more likely to lie about their birthplace than females? That kind of situation. So that's why gender will show up. I have gender showing up in the reporting model, not the true birthplace model. For the model on true birthplace, I've just got ethnicity and the kept variables again. So it's the same mixture model, it's the same hierarchical model, and the same editing and imputation model. So at the end of this stage, we've got a vector for updated gender and a vector for updated birthplace. They're complete and consistent. So the inconsistent monotone longitudinal pattern, we consider it as a repeated binary response, or so we have a single change point that's allowed. You're allowed to go from no to yes, but you're not allowed to go from yes to no. So some of the values can be deterministically imputed. If a student comes into the survey by 8th grade saying, no, I haven't had sex, and you can impute all the previous values to be 0. Same as if they've said they had sex on the last survey they took. The change point's already happened. It means you can impute all the values afterwards as yes, as 1. So the way this model works is we're going to model the time to this change point using a survival model. You notice that we have left, right, and interval censoring, because this is annual surveys. So this, they had this person report having or had sex somewhere between when they were surveyed in the 9th grade and when they were surveyed in the 10th grade. So I fit a Bayesian the survival model using this set of coefficients. So we've got the ethnicity, the age at entry, and the updated versions of true gender and true birthplace. I'm going to use the values, the regression parameters that are sampled to create a truncated normal distribution, and that's what I'm going to use to draw that predicted time of first sex out of. And where the censoring limits come in is to make sure that predicted value for time of first sex happen within the boundaries of the student report. So this is a subject, I'm looking at that was a subject level model, that survival model, but the variables themselves are, they're on each survey level, or they're on each survey. So for example, if I chose, or if I sampled a value, a time at first sex of 9.3, then all of the surveys prior to grade 9 are going to be set at 0, and all of them set at 1, or after grade 9, so 10, 11, 12 will be set at 1. So this editing and imputation model depends on if it was missing or consistent, and then what grade that specific survey is at compared to the time, the predicted time at first sex that was sampled. Now for this, if a record was identified as having an inconsistent pattern, the entire record was blanked out and imputed. And that's another spot for improvement in this model, is doing a minimal change model. So the multivariate responses, I'm going to look at, so the combination of knowing about and getting a Kahneman cap, we can look at it as like a 2x2 cell where this is a structural zero. This can't, for all intents and purposes, this cell can't, no one should be in this cell. So that's the joint distribution of it, where if 4 is the probability of going to get a condom on campus, and 5 is a conditional probability of knowing you can go get a condom on campus with conditional on not going to get one before. So the way these two are modeled is just with probit regression models. I'm going to model the probability of getting a condom on campus first, using the most updated versions of gender, birthplace, and ever having sex. And then conditional on the previous value for knowledge, I'll impute utilization. So if the previous value for knowledge is 0, of knowledge is 0, then the utilization, if they don't know about it, then they can't go and get a condom from it. But if they do know about it, then it's a random probability that they have gotten a condom from the cap. And then, then the model for knowing about the cap is also a probit regression model, the same set of predictors, but it's conditional on the current value for utilization. So the model for knowledge is conditional on utilization as well. So if the current value for knowledge is 1, if the current value for utilization is 1, then knowledge is set to 1. But if they haven't gotten a condom from the cap, then the probability of knowing about it is modeled as using that probit regression model. So the editing process here again is a joint edit. And the concept is to reallocate the students out of this inconsistent cell back into one of the 3 valid cells. And this is where we can consider the probability of making an error. So if a student really truly knew about the cap but didn't go get or knew about it and got a condom from it, that's a probability of going to get a condom from it, but then they made an error in the knowledge variable. So if they were observed, or if this is the true cell and they were observed to be in this cell, and they truly did know about it, they did not go to get one, but then they made 2 errors. So after normalizing these probabilities, you draw a multinomial random variable, and so you edit the pair the pair of variables at the same time based off of these probabilities. And again, these are sampled from using the previous probit regression models. So at this point, I'm just doing a simple aggregation of those cap variables across the surveys, so I could feed that back into the model for gender. And that whole cycle gets repeated for L iterations, or until these sampled values converge and stabilize. And then out of all those, I'm going to pull 20 samples and make 20 multiply imputed. So I have 20 multiply imputed and edited data sets. From there, I'll calculate the estimated proportions of interest for each of those, and combine the estimates using Rubin's rules. So we've got the first column is for the complete case proportions, and the deterministic editing, or the proportion under the deterministic editing where that's available, and then the proportion under the cyber mice after the algorithm, and with its associated confidence interval, because we did a random imputation and editing process. So we can see that, a lot of them remain relatively similar. That the deterministic editing definitely changed, made a higher proportion of females compared to the complete case or the cyber mice. The percent who've utilized the cap, got a condom from the cap, the cyber mice is more closely related to the deterministic edit than the complete case. And so the last 3 are the 3 valid cell proportions. So you see that it's lower than the complete case for going and getting a condom and utilizing it, or knowing about it and utilizing it, and higher here actually than either of the two. So this process edited more people out of that inconsistent cell into the didn't use it and didn't know about it cell, which is realistic for the population we're looking at. I mean, these are, even though a quarter of the kids in the sample are sexually active, like by 9th grade, getting condom rates are still relatively low.
Oh, sorry.
Yes.
I'm struck by the fact that your 95% confidence intervals don't include the complete case estimate in any case but twice. And they're really tiny intervals. I mean, those are really, really tight 95% confidence intervals. And you had stated earlier that the variance of the error is reduced unrealistically if you just use the mean.
Mm-hmm.
Do you have an idea if deterministic edits, just using the mean or imputing on the mean, produces even smaller confidence intervals, or are yours even tighter than those? How do you explain such really accurate estimates there?
I've not thought about doing the deterministic edit as like a mean type imputation. I haven't looked at these type of confidence intervals. It's a lot of these is there's a low proportion of inconsistent and missing, especially in these to begin with, and we are talking about 30,000 observations.
Which will shrink those down a lot.
Which, when you change, 5 variables, if there's a difference in 100 observations between, data set A and data set B, in the large wash for this example, it's not going to cause that estimate to vary very much.
Do you find it interesting or odd that the complete case estimate doesn't fall within your 95% confidence interval very often?
I don't find it odd, because this is literally dropping every single value that's inconsistent or missing, and so that's depending on the amount, expect, especially up in the condom questions, you're throwing out a lot of information.
And inducing bias. Indirectly, what that's saying is that the complete cases are not like a random subsample of all the cases, that there are connections between having missing items and some of the other outcomes, and that when you take into account the other outcomes, those are discernible biases that you wouldn't want to rely on. So,
Thank you.
but the concern about mean imputation, it seems attractive, but that as suggested will bias the variance estimates downward. So but you don't know whether the intervals are going to be narrower or wider when you do multiple imputation, representing uncertainty.
Mm-hmm.
Again, it depends on how well predicted the missing stuff is by the observed stuff. But when you're so far ahead with a strategy like this, why then backpedal and just stuff in a mean, which is artificial.
To me, the closeness between the deterministic edit estimates and the subordinate edits kind of not only justify that the models I used were not completely off base, because it's close to what that was generated after the research went through and said, this is what I believe the mechanism is, and this is how I believe we're going to change this. This just has, so the effect of making these changes is not too different than if we had a random component to it, but there's no measure of uncertainty here. So we're saying that these are complete. This is it's 13.7. There's no plus or minus. That's exactly how many kids used a condom or got a condom from the cap. So to kind of follow up on this, looking at the difference between a complete case analysis and analysis after performing this method, is, so I'm going to look at two separate models that you would run to determine like an intervention effect for this data. So I'm going to look at separate models for knowledge, for knowing about the CAP and getting a condom from the CAP. So separate models for knowledge and utilization. So this is on high school students only. They're both hierarchical. They both have random student intercepts to account for the student level clustering. And they use the same basic set of predictor variables, except that knowledge will have an indicator of ever having sex, and utilization is fit only on the sexually experienced students, only on the subset of sexually experienced students. Now, that indicator for ever having sex, that's a deterministic, or that's part of the Cybermice process. So every one of these complete and consistent data sets has a slightly different set of sexually experienced students, because that variable was imputed and edited differently across those data sets. So I fit these two models on the complete case and then each of the 20 generated data sets and combine result and run them all and combine the parameter estimates. So knowledge on the left, these are the wave variables. So T1 would be baseline. This is year 2, year 3, and year 4. So we get knowledge on the left, the utilization model on the right. And so the first thing that I noticed was that the Cybermice variable, the confidence intervals, are smaller, and for the most part, they're very similar to the confidence intervals that you would have got using complete case analysis. But in these starred cases is where the significance that you would, the association say, oh, it's, there's a difference between T4 here. Association, you say it's significant here, but not. You'd say it was significant in this complete case, but not in the Cybermice after performing that. So we can see here, complete case, T4 is higher than T1, but under the Cybermice, there is no difference between the 2 years, in capitalization across the 2 years. That did not work. That went all the way to the end. Oh, slowly going backwards. Nope. Apparently I can't use my knuckle. Sorry. Extra slides. Circle. One more. There. No. Oh, my word. Well, like I said, I guess I have to learn to use these. There we go. Comparison. That's the one I want. Before that. There. Okay, I guess I'm stuck at the end here. The intervals are smaller. Part of that is because there was a lot of, I'll say, not dropout towards the later end of the study, but more missing information, more missing values in the later years in T3 and T4 compared to T1. So the percentages were different. So so compared to for the full sample, the multiply edited and imputed data sets, this would be the model of knowledge, each year, so 890 cases were added compared to the complete case and from complete case data set. Each year, the number of cases that were added, or for the complete case analysis, the number of cases that were dropped increased across years. So there's definitely a time effect in terms of students who have inconsistent or missing data. And then for the sexually experienced sample, Again, that varies because that is a variable that's subject to the editing and imputation process, but it's still the amount of increase in terms of used observations for these models does increase over time. So that's definitely a function behind the smaller confidence intervals. And as I mentioned, if we look at the complete case, the estimated percent of students who know about the cap was 47.5 in year 4 compared to 41.5 in year 1, and that's a significantly different difference in proportions. But if you look at the estimates on the complete case, or on the multiply edited imputed data sets, we're now looking at a 43% versus 40%, which is not different. So, as you saw on the table, the variables that I used here don't necessarily have a large percentage of inconsistent or missing data. As you mentioned, the order of how the variables enter into the model is somewhat arbitrary. But it does fit. It does fit a story. I decided to choose to start with gender because the results led into birthplace easy and led into whether or not they ever had sex easier. And you wouldn't necessarily sit down and think, I'm going to predict gender based off of ever having sex. And importantly, too, these models, assume that the missing data is missing at random, but also the inconsistent data is inconsistent at random. And they're relatively simple models. There's a lot of other variables in the data set that would be used in models to predict either ever having sex or the cap variables. I stuck with these 5 just as to simplify the example, to get it going and to demonstrate that it works.
Sorry.
Yes.
Going back to Tom's example, say that when you say that the inconsistent data has to be inconsistent at random, what if we knew that there was an inherent bias to the inconsistency, as you had expressed, like the people knew they didn't want to say 10 sexual partners the next time? Does that meet your requirement of missing at random, knowing that it's biased in a certain direction?
I would adjust the editing models then to incorporate that information. So you could build that in. You would build that into your imputation or editing model if you know that these are not missing at random or not inconsistent at random.
Satisfy the assumption at that point. If you bias your assumption towards what you know.
Well, then you're not really using a model that you can say is, you're not using the assumption anymore that it's missing at random or inconsistent at random.
So you do just have to account for it then.
Yes.
It's a good question. The previous setting that I was familiar with these ideas was in the context of the census, where if you were imputing age from other information that might include the person's relationship to the head of household, the natural strategy was that if the head of the household was, let's say, 65 years old, and the person's relationship to head of household was child, you might take that and subtract 35 or whatever the right number is. But sometimes people get confused on the census, and instead of saying the relationship of this person to the person that's the head of household is that they're the child, they say that they're the parent. And so it turns out that when they were first doing imputation of age that way, that a majority of the people age 100 or greater in the census were imputed. And it motivated this idea of, well, it might be that a 100-year-old person is living with, but it might be 4 times out of 5 when you're doing 5 imputations. You might think that the error here was an editing error, and because there was a certain amount of relationship stuff when you had in both ages observed that you could make sense of that, where the person is age 30, but they're characterized as the parent of the person who's age 65 or something. But that seems like less of a likely scenario for somebody to try to hide something than sexual behavior. And but so long as you can condition on something else that's observed, this inconsistent at random is okay. It's only that if after conditioning on other things that are observed, if there's still some residual evidence of the person hiding something.
Mm-hmm. Yeah, the example you gave in the census, a lot of the editing stuff that they do came out of like operations research. It's still, I think they have some sort of, they definitely do a minimal change process. There might be somewhat of a random component in terms of like, well, okay, which one's wrong? Is it what did they mean child or did they mean, mother? But it's still a single. It's still a single edit process. But that's the at random also is trying to get at that there were definitely other variables that could have been used. Just the more variables you add, okay, this variable has missing. Is this variable inconsistent? Is it, and if you don't look for the inconsistency, if you don't think to do a crosstab of knowledge and utilization, you're never going to find that error. If you don't think to look at something over time, you're not going to find it. So it's really subject to having a very detailed-oriented data manager or data analyst who's going to look at it and pick it apart and say, what about this? What about this? What about this? Until you get sick of them, and then they end up doing something like this. So there's a lot of additions. A prior could be placed on the probability of making an error. I use the pi in the 2x2 chance, a 2x2 table for the inconsistent multivariables, but you could also put the probability of making a gender, an error in the genders, which could be a function of how many times they took the survey, how many times they reported, yes or no, or male or female. As I mentioned, the editing model, the monotone editing model could be altered to ensure minimal changes instead of just blanking out the entire record. But it could also be, this could also be used, like perhaps the variability in the editing and imputation results could be used to perhaps flag certain records of people who consistently report inconsistently, or you're just looking at this like, this person is messing with me, but that's a gut feeling, and I want to be able to have some sort of like, say, okay, if the variability in these responses is over this, then we're gonna examine that record and maybe take them out. Maybe that's not part of the sample that we're actually trying to get at or trying to represent. And that 2x2, the inconsistent multivariate framework, could also be used to model non-monotone changes between 2 time points. Instead of just going from no to yes and looking at it as a time to event, you could have any one of those cells be a structural 0. So overall, I introduced this method to mostly edit the inconsistent data while simultaneously handling the missing data. The confidence intervals around the model parameters in the example I gave were smaller, but they properly accounted for the uncertainty in those editing and imputation models. And even if there had been a lack of results, astonishing results, it doesn't mean that, or after applying this method, it doesn't mean that accounting for the uncertainty in these editing processes is unnecessary, just as it's necessary to account for the uncertainty generated in a random imputation process. You should account for the uncertainty in an editing process as well. And these are my dissertation committee people and project staff who this would have not happened without them. Any additional questions?
There's a couple, yeah.
Yes.
Oh, it's very applicable. So one question and one comment, is this some program in R or something that we can...
I wrote the entire thing in R, yes.
Okay. So is it going to be a library?
It's going to be a pack, yeah.
To get our hands on and...
Not in the necessary foreseeable future,
Okay.
but it has been similar packages like mice. Those are just for imputation.
Right.
They have been, they are available in various packages, like R and Stata. But it would, it's not unreasonable, but not at this time.
Just thinking is I can see a lot of applicability for the work we do here. So a comment too, I see an interesting application. This takes us in a little bit different direction, but with this whole move towards data collection online surveys and mobile phone data collection, a lot of times there are responses that we might want to flag as possibly inconsistent. And it would be an interesting application of this where even thinking before we want to automatically fill in inconsistent responses is just to flag it, how likely is this to be inconsistent. So I'm thinking in some of our studies, say, a person responds they're depressed on one question, but in the other questions they seem to be pretty happy in different measures. So we might want to flag that one response. It's kind of a silly example, but
No, it's not at all.
There's some others that I thought of that are more relevant. I just can't think of off the top of my head, but I think it would be tweaking that for another application.
And you'd still be able to capture the measurement response,
Right.
or the measurement error response in that as well,
Yeah.
because based off of this, on the next grant I worked on, we did computer-based survey. I'm like, nope, I'm not allowing them to make inconsistent, like I'm hard coding,
Right, yeah.
skip patterns, but then upon reflection, it's like, oh, you lose all ability for the measurement error at that point, because you didn't let them make the errors.
Right.
So, but that it works to, to flag it as a possibility.
Yeah, it's really, very applicable.
Great. Any other questions? Discussion?
I think this is like the most questions. Thank you guys so much. This has been like probably the most engaging talk I've given on this, so appreciate it.
We're a survey group. So
Exactly. That's very relevant.
Maybe one parting thought on Scott's. I mean, it's a challenge that we have to sort through where this is a discipline. Like when you have a dissertation project where there's a lot of development of computing methods, but they're really to make it available as a package would require a lot more effort on the part of the student, and yet there's really actually a lot of quality stuff that if it were made more accessible, if the resources were there somehow, but I don't know quite how to do it.
Maybe write a grant.
Yeah, you gotta have some funding mechanism to support yourself to go to that next step.
I know the National Cancer Institute, they have a push for making things available to researchers, and on one of their web pages they even have a phrase about bringing software development to another level where researchers can actually use it. So.
Yeah, I mean, I think the logical thing would actually be if you could get funding for a postdoc year.
Mm-hmm.
That would be it would have multiple purposes, but might include that. That would be the natural time to do this right after you're done. So, of course, some people might want to move on with their lives more quickly. But having a postdoc, I was a postdoc. I know Rob was a postdoc. There are worse things in the world than being a postdoc. So.
I think the first next step for this is a simulation study, though. Yeah. And I'm going to be written into, because I'm going to be teaching in the fall at California State University, and I'm going to be written into their grant proposal for research in undergraduate teaching, like summer workshop kind of thing. And so I'm going to kind of try to I don't say push this, but this is one of my things, is to get a simulation study, because there's sort of guidelines around missing data. It's like, oh, if you have over 10%, if it's under 10%, then whatever, we don't care about it. Just drop it. There's no real guidelines for inconsistent data. It's like, is there that same kind of threshold? How important is the mechanism? Is it just as if you really misspecify the imputation model, how bad, or editing models, it's just as bad as misspecifying the imputation model. So that's kind of where I want to go first before it's like, hey, because it's got to be worthwhile. This was not the ideal data set to demonstrate the awesomeness of this technique. So if I construct one where I know here's the specific problems, does it actually, how well does it work? That kind of stuff.
Yeah, well, I'll add one other tidbit on that point, is there was because you were saying there wasn't very much missing data. One strategy that we used in a project was Bernard's, Bellin, and Schaefer. We were thinking about, suppose you use a multivariate normal imputation model to fill in missing binary values, and so we had some different ways you considered rounding or coin flipping with something like that. with a predicted value, imputed value as a probability. But the way we did that, the simulation was based on a data set that had 100,000, it was a large survey of like 100,000 teenage kids, and percentage of missing data, kind of percentage of cases with any missing values was 3 to 5%, something like that. So it wouldn't have by itself been that compelling, but what we did was we said, okay, let's let the complete cases from this large survey be like a large finite population that for this simulation study purpose, we're going to assume is the population. And then we'll sample from that to certain sample sizes, and then we'll also impose missing data patterns, but instead of like doing a logistic regression model, what we did is we just took the 3 to 5%, whatever they were, the incomplete cases, and we said we'll just borrow missing data patterns from those cases, and we'll let the percentage of cases with any missing values be a factor in the simulation study. So we had, I think we did 25% or 50%, because it wasn't 25 to 50% missing data, but it was 25 to or 50% of the cases had some missing value, because that would then be able to show the impact of a difference in the procedures more readily than if you only had 3 to 5% missing, just because of the complete cases dominating it. So that was a way to kind of to make use of a large data set and separate things out and finesse the issue of how to generate missing values in a simulation experiment, because all of the patterns were realistic because they're all real.
Yeah.
So that you might actually consider
that. Thank you.
Yeah.
It's a lot. Yeah, I like that. So. Well, thank you again.
Yeah, thank you.